Okay, so now that we have discussed the tangent and normal vectors, what we want to do next is relate the acceleration to those two vectors. So how can you break up the acceleration in a useful way in terms of the tangent and normal vectors? So let me just say that this will also be related to the concept of curvature. So we are going to figure out now what that's supposed to mean. Reminder, the tangent vector was the velocity vector divided by the speed of the particle. The normal vector is the derivative of the tangent vector divided by its norm. And remember that by construction, they happen to be perpendicular. So in a sense, you should think of this as a rotated version of the vector I, and this is a rotated version of the vector j. And they can be changing their positions as you move along the curve. Okay? I'll do an animation in one of the videos so that you see eventually how all the three vectors, there's another one left called the binormal, and you'll see how they all interact. Now, what's the acceleration? The acceleration is just the derivative of speed. But let's write this in a more useful way because we want to relate this to the tangent and normal vectors. So that's the derivative with respect to time. Sorry, the derivative of velocity, I meant. That's the derivative with respect to time of velocity. But if you see, velocity can be rewritten as speed times the tangent vector. Right? And now you apply the product rule. This is just like a function, a scalar function. So this is just, the product rule says this is the derivative of speed with respect to time times the tangent vector. So there was a small glitch. I was just saying that you have to apply the product rule here. When you apply the product rule here, you get the derivative of the first term, which is the derivative of the speed times the tangent vector, plus the speed times the derivative of the tangent vector with respect to time. But now, in order to interpret this, you can just use the fact that the derivative of the tangent vector with respect to time can be obtained from this equation just by multiplying both sides of the equation by this denominator. And so you can just substitute this this term with this one. Okay? And so what you find is that the acceleration is this term plus this term. The thing is, like, the first term is a term which is a multiple of t. The second term is a multiple of n. So what that means is that the acceleration breaks into a component, like again, t and n are like I and j. It's just that they're changing as you move along the curve. So what this is saying is that the acceleration breaks into a component which is parallel to the tangential vector, which we call the tangential acceleration. And it also breaks into a component which is parallel to the normal vector, which we call the normal acceleration, unsurprisingly. Okay? So, in other words, what we have is that the acceleration breaks into two pieces: the tangential acceleration, which is this one, and the normal acceleration, which is this other one. And so, maybe to make a picture, what I'm trying to say is that maybe you have here the curve. The tangent vector is here. The normal vector is here. And then the acceleration is just basically a sum of some rescaled versions of the tangent and normal vectors. So the acceleration of the particle, in this case, will look maybe something like this. Okay? Because again, like you rescale the tangent vector by some factor, which is this one, and then you rescale the normal vector by another factor, which is this one, and the sum of those gives you the acceleration. And another point on the curve, maybe here, maybe here's the tangent vector, here's the normal vector, and again, some rescaled version of these two will give you back the acceleration. Okay? So, in a sense, as you move along the curve, you have these two perpendicular vectors, which are the tangent and the normal, and they create a plane, right? Two vectors will determine like a plane, and the acceleration is always in the plane determined by these two vectors. So they move something like this. Okay? Now let's try to interpret this in terms, let's try to see what this notion of curvature is and how it appears from this perspective. There are other ways in which you can sort of find what curvature is supposed to be, and you can check the PDF for that, but I decided to take this more kinematical approach, seem more fun. So the tangential acceleration, as the word suggests, right? If this component is entirely responsible for accelerating the particle in the direction where the motion is taking place, right? Because the motion is taking place in the direction of the velocity vector. That's where you want to move, right? If there's no acceleration, a particle would just follow a straight line determined by the velocity vector. So instantaneously, the tangential acceleration is just trying to increase or decrease that velocity. Okay. On the other hand, the normal vector, the normal acceleration is perpendicular to that. So that's really what's doing the bending, right? Because the other one is parallel to where the motion is taking place. The normal acceleration is actually the one that will move you to the right or left, depending on how the perspective that how you're thinking about the motion. So really, the normal acceleration should be the one that's somehow related to the bending of the curve. Okay. Okay, and so how is this going to happen? So in a sense, this is really what's going on. We just want to extract a number. We want to measure this bending in a quantitative way. We just don't want to say something like, oh, it's just bending. No, we want to sort of measure how much it's bending. So we'll try to get it from the acceleration, from the normal component of the acceleration. So notice that what are the units? Again, this is an acceleration, so an has units of length over time squared, right? Those are the units of acceleration. On the other hand, what are units of the speed, right? Is length over time, and this has no units, right? And the other one, this has units of 1 over time. So this makes sense because that has units of 1 over time. So this makes sense because the the product of these two units should give you back this one. Now, on the other hand, let's see. So on the other hand, for a curve, right? I mean, both of these. This thing is more related to the particle itself, and this thing has units of 1 over time, which doesn't play nicely with the curve, because the curve, I mean, if you want to associate something to the curve, it should be more in terms of distance units, like feet or meters or miles, because time is sort of more of intrinsic to the particle, not to the curve. So what I'm trying to say is that you can relate time and distance, right, through speed, right, because the units of speed are distance over time. So you can do this following trick, and you can use speed as a conversion factor between time and distance. That's what I'm trying to say. So you can rewrite, notice that you can take this formula for the normal acceleration and rewrite it this way. Right, so what I did was multiply and divide. Notice that this is the same expression because I just multiply it and divide by the speed. So one of these factors can cancel the one downstairs, and you just get back the same expression. Okay? But what's the net effect of doing this? The net effect is that now this quantity, right? What are the units of this quantity? Well, this has the units of inverse speed, right? So this is time over distance. And this part had units of 1 over time. So the time units cancel, and you just get 1 over distance. So this now does have units of 1 over distance, and what we wanted was something which was related to distance units. So this seems to be an interesting quantity, and in fact this is what's known as the curvature. So what I'm trying to say is that one defines a curvature as this is like a K, but it's like a fancy Greek letter K called kappa. Those of you who are interested in fraternities may know this letter. So curvature is 1 over speed. Okay? And with this formula, then the normal acceleration becomes, with this formula for curvature, the normal acceleration becomes the speed squared times the curvature times the normal vector. Okay? So again, curvature has units of 1 over length. And so in the next video, what I will do is do some examples of computing curvature for some simple curves so that you actually see that is somewhat of a reasonable notion of curvature. Again, there's a more geometric way to derive it, but here it's just sort of appearing. We already knew that this one had to be, this quantity or this vector had to be related to the bending of the curve. So we're just trying to find a natural term in this expression that could have just units of distance or a power of distance, so that we can use it to measure some geometric quantity of the curve and not the particle itself, because time is more related to the particle, to the motion of the particle, not to the curve.